reflection show who I am inside.
For this question, we are going to a different source, that is Giancole Physics for Scientists and Engineers. We are investigating a fiber optic cable that is hit by a beam of light at some beginning angle alpha. And it is going to refract into this, strike this wall of the fiber optic cable, and because it's a fiber optic cable, we want to figure out how to make it stay inside the fiber optics. So to do that, there's a specific angle at alpha that is maximum. After that angle, this beam is going to start refracting through as opposed to bouncing back and total internally reflecting. We label some other angles to make this calculation more clear, alpha, beta, and gamma, and we know the index of refraction to be equal to 1.42. So let's work backwards from this final point. Let's ask internal reflection. What does that correspond to? That means that even if this beam of light were to exit the material, it would have an angle from the normal that's greater than 90 degrees. And knowing that our object kind of stops being a transmission at above 90 degrees, we see that to be phooey. We see that to be ridiculous. Like, no, we cannot move beyond 90 degrees. So instead of being transmitted and refracted, instead of the light being bent out of the material, it is just reflected back into the material. So we then ask, how do I know at what angle a beam of light is refracted? To do that, we go to Snell's law. And in this case, theta 1 and theta 2 are going to switch back and forth between alpha and beta and gamma and all those, but this is the incident angle from the normal, and this is the outgoing angle from the normal. So in doing these problems, we have to identify what's going in, what's coming out, what the indices of refraction are for both of those, and then solve for what we don't know so that it fulfills this law. So we're going to call this point A, and we're going to call that one point B. So at point A, our N1, our incident index of refraction, is our beam inside of the fiber optics. So it's 1.42. Our outside is air, and air has an index of refraction of 1. It's very similar to that speed in a vacuum. So our inside angle, theta 1, is going to be gamma, as we've labeled it. Our outside angle is going to be, based on our statement of total internal reflection, 90 degrees. This is the point at which we can no longer get any sort of actual refraction. It's just skimming along the surface. So we say, all right, I know everything numerically except for gamma. So I can use this to solve for gamma. Doing it just that. 0.42 sine gamma is equal to 1 times sine of 90 degrees, which we know easily, due to our extensive practice with trig, to be just 1. That is our y value when theta is 1. And we divide by 1 over 1.42. We solve further for gamma using an inverse sine, and we get this which is numerically equal to 0.7813 radians. Knowing this, we can move forward in the problem, saying that, all right, we know what gamma is. I can move now closer to my beginning, which is beta. So I'm going to expand this triangle a hair. Looking at this triangle, we can identify this as a right angle, because the way we drew our normals, our normal here is perpendicular our normal here, because it's just a nice rectangle. And knowing that that's 90 degrees, we can know the relationship between the two other members of the triangle, either by saying, oh, they're complementary angles adding up to 90 degrees, or by saying all three angles add up to 180 degrees. I'm going to go with the former because it saves us a little time, and it shows us that beta is equal to 90 minus gamma. Or, to make it more commensurate with our units, we're going to use pi over 2 minus gamma. So I move down to where I have progressed and say now that beta is equal to pi over 2 minus gamma. Beta is equal to 0.9234 radians. Cool. Progress has been made, and now we look to see, all right, I now need a relationship between alpha and beta. This is often how these problems go. You'll move from one part of the geometry to the next, gradually picking out what you do and don't know. So alpha and beta are both incident at the same place. They represent parts of the journey of this ray of light, parts of its lifeline, and we want to connect them with the unstoppable laws of the universe. And the particular one here is Snell's law, which we know very well. So we won't stop them. We will just say, all right, we're now at point B, and we are identifying all of our angles and indices of refraction. So we can use Snell's law. Our outside, in this case, our incident, is air. So this is 1. Our inside is now 1.42. And theta 1 is equal to our alpha, our incident, and theta 2 is equal to beta, our outgoing, our wave that is in the fiber optics. In this case, we know beta to be 0.9234 radians, and we don't know alpha. We're trying to find alpha under the constraint we stated previously, which is that we still want total internal reflection to occur. So we go ahead and we say the same thing we said before, and move forward to solve for alpha. A sine of all of that stuff. Oh my gosh. Optics is a slog algebraically and never produces anything beautiful. Just like my childhood. Just kidding. It produced a human being that can do physics, and that's all that childhoods are good for, said my father. Just kidding. My dad is an auto mechanic, fun fact, which is basically just knowing how to do everything in physics without any of the, like, bougie vocabulary. I still can't change my own oil, though, so I don't know what my childhood was actually good for. No resentment, though. I love my dad. He's a cool guy. So it looks like I made a little error in my value of beta. We will correct that. So we notice something interesting here. When we plug this in arithmetically, it's going to give us about 1. It's going to be very close to 1. And we say arcsine, asine, sine inverse, whatever you want to call it, that's asking for the angle when our argument is equal to 1. And we know that for sine, that's going to be true when we're at pi over 2 radians or 90 degrees. So this is a little peculiar because what we were looking for is the angle alpha for which this beam gets totally internally reflected, meaning that when the angle alpha is equal to 90, even then the beam will go in and be totally internally reflected. It will refract and then bounce off the walls of the cladding. So what we actually discover is that for this material, if light comes in at 90 degrees and then maybe goes down to like 80 degrees or something, at 80 degrees, our angle alpha is going to be smaller, which means beta is going to be smaller, which means gamma is going to be bigger. And if gamma gets bigger, that means that we go even further than 90 degrees. Again, I'm going to restate that just to emphasize. We have alpha getting smaller, beta getting smaller, gamma getting bigger, and our condition for total internal reflection being better fit, being pushed past 90 degrees, which means that it's more easily or more like, I guess you can't be more yes of something, but it is yes also total internally reflected. It is so yes totally internally reflected for any alpha less than 90 degrees. And if alpha is less than 90 degrees, that's pretty much every single alpha that you can think of. So for this material, we have an interesting conclusion. Implies it's always total internal reflection. Cool. So that is the twist ending to this Canterbury tale of intrigue and betrayal, perhaps, if you were expecting something other than 90. I'm sorry, dear reader. Things aren't always as they seem. So, recapping, we drew a picture of the problem, labeling all of our angles. We labeled some points to make sure that we knew what we were doing there. We figured out how gamma relates to 90 degrees, giving us a starting point in terms of something that we know. It's 90 degrees because of total internal reflection. We see how gamma relates to beta using some basic trig. We see how beta relates to alpha using Snell's law once again. There's our first Snell's law, and here's our second Snell's law. And we arrive at this answer of pi over 2 radians, which we figure out means always total internal reflection. Good.